And before we go into the other representations, I just want to show you another statement that we can use to represent the same logic as we did in our first block, but without the need of writing it inside a process. We can do this one like this. So we can say with, this is a with statement with m input, select, and then we say majority gets 1 when, and here we enter the same cases as we had before on the other table, because it's pretty much we are just writing the same thing, just using a different statement. So this one is 101, and then when 110, and when 111, and we end with a semicolon. So you can notice that here the statements are separated by commas, different from the case statement. Oh, and wait, I'm missing one statement here. I am missing my zeros, which is when others. So this completes our logic. So in this case, you can see the difference. This with statement is a lot more compact than the case statement, but also it doesn't need to be inside a process. So that's our second architecture. Now we'll move on into implementing the Boolean formula in order to write our third architecture block. Another way to express the logic of our circuit is using a Boolean function like this. This can come up as a formula that you're given as a circuit, or as a you can extract this from the truth table. So the idea is that we can turn this formula into statements that can describe that directly into the architecture. So let's write another architecture block. I'm going to call this one behavioral 3, and this is majority, and we are going to declare some signals. Okay, so I'm going to declare some signals here, and these signals are going to represent the combinations, these AB, AC, BC, and AC, just for simplicity. So I'm just going to call them AB, AC, and BC, and all of those are going to be in standard logic because they're single bits. Okay, and I believe that's all we need. So we can say that AB first and foremost gets M input, because remember this is our input, M input 2, and M input 1. So that means it's taking 2 of the input bits and it's ANDing them together, right? So next I'm just going to copy and paste this because it'll be easier. Now BC is going to be input 1 because that's B, and then C is 0, and then AC, I'm going to say A is 2, and then C, as I said before, is 0. So this way we have assigned our AND functions already. Okay, so now let's do the OR function, but we don't need to create a signal for that because that way we can just assign it to the output. In this sense, we just say that the majority output equals AB or BC or AC, and that's it. That is another way to write our architecture.